When people talk about upgrading a PC, one of the first things that comes up is RAM. But RAM didn't just magically jump from a few megabytes to the ultra-fast DDR5 we have today. It evolved step by step, with each generation solving real problems from the one before it. So in this video, we're going to walk through the full evolution of computer RAM, starting from SDRAM all the way to DDR5 in a simple, clear, and practical way. Before we jump into the different RAM generations, there are two things you need to understand. First is RAM speed, which is commonly called megahertz, but is technically measured in mega transfers per second, or MT per second. This affects bandwidth, which is simply how much data the RAM can move every second. Think of bandwidth like a road. Higher bandwidth means more data can travel at once. Second is latency, shown as CL. This is the delay between your CPU asking for data and the RAM responding. So in simple terms, bandwidth is how much data moves. Latency is how fast it responds. This is why higher MT per second alone doesn't guarantee better performance. The best results come from a balance of good bandwidth and low latency, and that balance is what each new RAM generation improves. Now that we've got those basics out of the way, let's rewind to the late 90s and see how all of this started. SDRAM. Before DDR even existed, most PCs in the late 1990s used SDRAM, which stands for Synchronous Dynamic Random Access Memory. This RAM synchronized itself with the system clock, which was a major improvement over older memory types. SDRAM typically ran at 66 to 133 megahertz, and most systems had 64 megabytes to 256 megabytes per stick, which sounds tiny today. At the time, this was enough for operating systems like Windows 95, Windows 98, and Windows ME, basic web browsing, office work, and simple games. The biggest limitation of SDRAM was that it could only transfer data once per clock cycle. As CPUs became faster, SDRAM couldn't keep up, and processors spent too much time waiting for data. This limitation led to the next big leap in memory technology. DDR1. Around the year 2000, we got DDR1, or double data rate memory. The key improvement was in the name. DDR could transfer data twice per clock cycle, once on the rising edge and once on the falling edge. DDR1 typically ran at 200 to 400 MT per second, with common capacities ranging from 128 megabytes to 1 gigabyte per stick. Voltage dropped slightly to around 2.5 volts, helping reduce heat and power consumption. DDR1 supported operating systems like Windows XP, which was much heavier than previous versions. It made multitasking smoother, reduced game loading times, and improved overall system responsiveness. However, as software and graphics became more demanding, DDR1's bandwidth wasn't enough for newer CPUs and GPUs. DDR2. In 2004, DDR2 was introduced. This generation focused on higher bandwidth and better efficiency, not just raw speed. Speeds increased to 400 to 800 MT per second, with voltage dropping to around 1.8 volts, significantly reducing heat output. Memory capacities grew to 512 megabytes to 2 gigabytes per stick, which was considered massive at the time. DDR2 was commonly used with Windows Vista, an operating system that required much more memory than XP. Although Vista had performance issues, especially on low RAM systems, DDR2 helped improve multitasking, web browsing, and basic photo editing. One drawback of DDR2 was higher latency, meaning it took longer to access data. So while bandwidth improved, efficiency still wasn't perfect. DDR3. In 2007, DDR3 arrived and became one of the most widely loved RAM generations. DDR3 improved not just speed, but also latency efficiency, which is why systems felt noticeably smoother compared to DDR2. DDR3 speeds typically ranged from 800 to 1600 MT per second and later even higher. Memory capacities increased to 2 gigabytes to 8 gigabytes per stick, and voltage dropped to 1.5 volts, with low-power versions at 1.35 volts. DDR3 paired perfectly with Windows 7, which was better optimized than Vista. This combination delivered smooth multitasking, faster game loading times, and solid performance for video editing and productivity. Because of its balance and reliability, DDR3 systems stayed relevant for nearly a decade. DDR4. DDR4, released around 2014, focused on efficiency, stability, and higher memory capacities. Speeds started at 2133 MT per second and commonly ranged up to 3200 MT per second and beyond. Voltage dropped further to 1.2 volts, resulting in cooler systems and better power efficiency, especially for laptops. Memory stick sizes increased to 4 GB, 8 GB, and 16 GB, making 16 GB total system RAM the new standard. DDR4 powered systems running Windows 10 and Windows 11, handling modern gaming, streaming, multitasking, and content creation smoothly. Even today, DDR4 still offers excellent real-world performance for most users. DDR5, released around 2021, introduced major architectural changes. Speeds start at 4800 MT per second and can exceed 7000 MT per second, delivering significantly higher bandwidth. DDR5 also supports much larger capacities, with 16 to 64 GB per stick becoming common. Voltage drops again to around 1.1 volts, improving efficiency despite higher speeds. A new feature in DDR5 is on-die ECC, which helps correct small internal memory errors. This is different from server-grade ECC, but it improves stability and reliability. DDR5 benefits high-end gaming, heavy multitasking, large code compilations, and professional content creation, though it comes at a higher cost and offers smaller gains for casual users. Dual-channel memory. Dual-channel memory means using two RAM sticks together to increase memory bandwidth. This is why matching RAM sticks, same size and speed, is important. Dual-channel is especially beneficial for integrated graphics, where the GPU uses system RAM instead of dedicated video memory. More bandwidth directly improves graphics performance. RAM compatibility. RAM generations are not backward or forward compatible. DDR3 won't fit into a DDR4 slot, and DDR4 won't work in a DDR5 motherboard. Your CPU and motherboard both must support the RAM generation you use. Desktop PCs use DIMMs, while laptops use smaller SODIMMs. By default, RAM often runs at a lower speed than advertised. To enable full speed, you must turn on a memory profile in BIOS. XMP for Intel systems, Expo for AMD systems. These profiles allow RAM to run safely at its rated MT per second speed. Now the question is, how much RAM do you need today? 8 GB is the bare minimum for the modern systems. 16 GB, ideal for gaming, multitasking, and everyday use. 32 GB, best for programming, streaming, video editing, and heavy workloads. Adding more RAM doesn't automatically increase FPS. Once you have enough memory, performance depends more on your CPU and GPU. So the conclusion is, DDR4 is still more than enough for most users, offering excellent performance and value. DDR5 is best for high-end systems and professional workloads that can actually use the extra bandwidth. Over time, DDR5 will become mainstream, and eventually DDR6 will arrive to start the cycle again. If you found this explanation helpful, make sure to like the video, subscribe for more tech content, and let me know what PC topic you want covered next. Thanks for watching, and I'll see you in the next one.